Okay, so we've been talking about sine and cosine for a week now. Let's start looking at the graphs of these functions. That's what today's lecture is going to be about. And let's start with sine. So I endeavor to graph sine of t right now. And in order to do it, well, how about we just use the most basic rudimentary graphing technique we know, which is just plot points. So I'm just going to pick some points. I'll pick points for which we can calculate the sine exactly. And why do I have a picture of the unit circle here? Well, the unit circle is how you can figure out what the sine of these points are. So I just included the unit circle right here as an aid to help us calculate some various values of sine. So, okay, what values should I choose? Well, let's start, how about with sine of 0? So that would correspond to this point on the unit circle. And remember, the sine is the y value. So the y value that corresponds to the point on the unit circle with angle 0 is 0. And let's see, how about the next one? Let's do pi over 6. So now there's an angle of pi over 6. And once again, as I said, the sine is the y value. The y value corresponding to an angle of pi over 6 is 1/2. So I can put in 1/2 or 0.5. Okay, now I'm going to plug in a whole bunch more points right now. In the interests of time, I'm going to do it rather fast. So if this goes too fast for you to fully keep up with how I was able to get all these values, then maybe you can just rewatch this video at a later time. But I'm just going to quickly list off a bunch of points here. So let's do pi over 4 and pi over 3. And how about pi over 2? And how about 3 pi over 4? And let's see, how about pi and 5 pi over 4? Let's see, it's 3 pi over 2. Let's see, 7 pi over 4. So I'm doing this angle, 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 and writing down all those y values. And I'm just going to do this kind of fast right now. At pi over 4, it is root 2 over 2, which is approximately 0.7. At pi over 3, it is root 3 over 2, which is approximately 0.9. At pi over 2, it's 1. At 3 pi over 4, that's root 2 over 2, which is approximately 0.7. At pi, we're back down to 0. 5 pi over 4, it's negative root 2 over 2, which is negative 0.7. 3 pi over 2, we are at negative 1. At 7 pi over 4, that's negative root 2 over 2, which is approximately negative 0.7. And after that, let's do 2 pi. So 2 pi corresponds to a complete revolution, putting us back at where we started. So we're back to the y value being 0. Now I can go even beyond 2 pi. How about, let's see, what's after that? 9 pi over 4. 9 pi over 4 is coterminal with pi over 4. So I've completed a revolution, and I'm now back to angles which I already calculated the sine of. So at this point in filling out the values, they're going to start to repeat. I don't have to like keep on doing this this plugging in that I've done because I already know what I'm going to get. So at 9 pi over 4, I'm just going to get the same number I got at pi over 4, which is about 0.7. And let's see, I can even plug in negative angles if I wanted as well. Like if I plugged in negative pi over 4, that would correspond to moving in the reverse direction, and I would get negative root 2 over 2. But to address this issue of the values repeating once I go around a full 2 pi, let me give you a definition, okay, before I start plugging in these points. And that definition is a periodic function. So suppose that g of t is a function. Suppose that p is some number such that the following holds. G of t plus p is the same as g of t for all t. In that case, then we say g is a periodic function, and its period, that is how long until it repeats, is whatever that number capital P is. Okay, so due to the fact that sine repeats itself after every 2 pi, that is after a complete rotation, here's a fact: sine of t is a periodic function of period 2 pi. So I'm going to use that to help me draw the graph. Now, let me plug in all those points that I calculated the sine values for. Okay, so let's see, this is where I need some art ability. Okay, so let's put some angles on this graph. Let's say there's pi, 2 pi, 3 pi, negative pi, negative 2 pi, and let's say that this is 1, and there's negative 1. Okay, so now I'm just going to start plotting all the points that I calculated. So let's see, at 0, it was 0. Let's say if there's pi over 2, at pi over 6, it was 1/2. And at pi over 4, it was 0.7. Pi over 2, it's 1. 3 pi over 4, it was 0.7. At pi, it was 0. Say here's 5 pi over 4, it was negative 0.7. At 3 pi over 2, it was negative 1. And okay, I think I've got enough points plotted that I can kind of infer what the general shape is going to be. So smoothly connecting these points, I've got the shape of my sine graph. But now I can exploit the fact that it's periodic. So here's a little quick demonstration of what it, oh wait, I made a typo here. What the heck is that? Okay, so here's a quick demonstration of how to graph a periodic function. Let's say that you've got a periodic function that looks like that. Well, to graph the rest of it, just take rigid copies of the part you already graphed. So the next portion of the graph will look like that. The portion after that will be once again a rigid copy of one full period of the pi. I can even extend it to the left as well. So that's how you graph a periodic function. So I already know what the rest of the graph is going to look like. It's just going to be rigid copies of the part I already drew. Cool. Juliet.
I had a question why sine was like restricted on the y-axis on like 1 and -1. Like why is it just only there?
Yeah, so if you look at the unit circle, remember sine is the y value of any point on the unit circle. But what's the biggest y value you can see on the unit circle? It never goes above y equals 1. And it never goes below y equals -1. So yes, good point. The sine is rigidly trapped between -1 and 1. It can never go above 1 or below -1. So in fact, that tells me what the range of sine is. Let me write that right now. So the range of sine of t is, as Juliet just pointed out, the interval from -1 to 1, including -1 and 1, because it does actually hit those values. The domain of sine is all real numbers. We can plug in any number, right? This graph extends forever to the left and to the right. How about the zeros of sine? So I don't know if any of you have looked at the latest homework assignment, but if you have, you'll notice there's some questions where I make reference to this, and I'm going to talk more about it once we get to inverse trig functions. But let's say I asked you, where are the zeros of sine? So I want the points where the graph hits the x-axis. In other words, right there, 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 and so forth. Let me get a yes or no. Sine t has an infinite number of zeros. Oh, good. Okay, all right. This seems to be pretty uncontroversial. The answer is yes. Yes, it does. And where are those zeros? Okay, so let me start listing them. The zeros of sine are at, okay, let's see. Well, they're at 0 and pi and 2 pi and 3 pi, so forth, and also negative multiples of pi, like a negative pi, negative 2 pi, negative 3 pi, etc. i.e., I could more compactly describe all the zeros as follows. How about I just write k times pi, where k is any integer. Yeah, so any multiple of pi, any integer multiple of pi. Those are exactly the zeros of the sine function. And that's kind of a more compact way to write it. Oh, let me point out one more fact about the graph. If you look at the graph, there's a lot of symmetry going on in this graph, and I'm going to discuss a number of aspects of it today. One is it's symmetric about the origin, which is a property of an odd function. So let me point that out. We already knew that. I've already mentioned that, but notice the symmetry about 0, 0, i.e. sine t is odd, i.e. sine of negative t is negative sine of t. Okay, so now I'm going to show you an animation, sort of a dynamic demonstration here. So I want you to imagine that you're a point on a circle that is moving around the circle at a constant angular velocity. Okay, like let's say you stick a push pin in a bicycle tire and spin the tire and just watch where the pin goes as the tire spins. And let me get rid of some elements that we don't need in this graph. Don't worry about tangent or cosine yet. Okay, so oh wait, there you go. So you're just spinning around the unit circle at a constant speed. Okay, now I want you to keep track of what the y value is as you're a point on this circle. I think I can even check this out. There we go. So keep track of the y value. Let me show that. Let's see where. No. There. Okay, there. That blue line is your y value of the point on the unit circle that we're keeping track of. But that's the same as the sine of the angle, right? So now let's make a plot of that y value as a function of time. And what that will look like is the sine graph. Here, so let me start it from the beginning. So we start with the y value being 0 when the angle is 0. And as the angle increases, the y value goes up. Now the y value starts getting negative, and we end up back at the y value that we started at. So there's a graphical animation of what the sine value is doing. Okay. Now, let's see, we have some chat questions. Now having graphed sine in a lot of detail, now let's move on to cosine. So I'm not going to go through the whole rigmarole that I just did for sine for cosine. Okay, much of it will be the same. But in fact, we can use this animation because the cosine of an angle is the x value of a point on the unit circle. In other words, let's see, let's look at the x values now. No. There. That little red line is the x value of the point on the unit circle that corresponds to a certain angle. So now let's make a plot of the x values over time. And that will be the red line. So we start with the x value being 1. So this red line is equal to 1. And as we move around the unit circle, sorry, let's turn off the sine for the moment. Turn on the cosine. There we go. As we move around the unit circle, the x values, now they're negative, and after making a full 2 pi rotation, the x value ends back up at 1 where it started. Okay, so that is your cosine graph. So let me make a plot of that now. So let's see, the cosine graph, say here's 1, negative 1, pi. Cosine graph, without going into full details here, it starts at 1, at pi it's negative 1, it crosses the x-axis at pi over 2, and there's your cosine graph. And again, I can, as we say, extend it periodically. So it's just going to keep on doing what it's doing. And great, okay, so there's our cosine graph. We noticed one thing right off the bat. So for the same reason as with sine, cosine t is periodic, and again of period 2 pi. Oops. And the domain of cosine is the same as the domain of sine. All right, again, it's trapped. Sorry, again, you can plug in any real number. So the domain is all real numbers. And the range, well, the cosine graph, it looks a lot like the sine graph. And again, it's trapped between negative 1 and 1. So the range is negative 1 to 1. Here's another fact about the graph, which maybe you can tell by looking at it. And it's actually something we already know. So notice the graph is symmetric about the y-axis. i.e. cos t is an even function. i.e. cosine of negative t is the same as cosine of positive t. Okay, Valentina.
Right, so the zeros are every pi over 2.
Oh, good question. Wow, that is an astute question. Nice. So you do have a 0 at pi over 2. Um, where where is this 0? That's at the point. What's the x coordinate at this second 0 of cosine? Can someone tell me? What's the x coordinate right there?
Is it -1?
The the -1, that so -1 is the minimum value of cosine, but here I want the y value to be 0. The x value, it's between pi and 2 pi.
3 pi over 2?
It is 3 pi over 2. That would be, if we go up, let's say, to the unit circle for a moment, at 3 pi over 2, the x value is 0. So that's the second 0 of cosine. The first one happens at positive 3 pi over, sorry, at positive. First one happens at pi over 2, that is to say. The second one happens at 3 pi over 2. And then they just repeat every 180 degrees. So if I wanted to list the zeros, and I'm not really supposed to talk about zeros today because that's more of a topic next lecture when we start talking about inverse trig functions, but because it's such a good question, I'll answer it now. So the zeros happen at pi over 2, then 3 pi over 2. Maybe some of you can spot the pattern already. The next 0 will be at 5 pi over 2, and then 7 pi over 2, so forth. So it's odd multiples of pi over 2. And I could also include negatives, negative pi over 2, negative 3 pi over 2. You could write it as pi over 2 plus any multiple of pi. So yeah, that's a really good question. We'll talk more about that tomorrow. But let me first get down some more basics about the shape of these graphs. So let me turn to Desmos again. And, oh, actually, here, you know what, forget this. Okay, so let's start off comparing sine and cosine. So there's sine x, there's cosine x. They look kind of similar, right? How similar are they, in fact? So how about, instead of cosine, let's look at cosine of x minus a. And here, let's let a go from 0 to 7. Okay. So there in green, you can see cosine. In red, you can see sine. And as I start translating cosine to the right, let's see what happens. Right at about 1.56, it looks like it's lying exactly on top of sine. Huh. 1.56. Where the heck did that number come from? Is that just a coincidence? Any idea what this A of 1.56 is exactly?
Is it pi divided by 2?
That is pi over 2. Yes, exactly. Good. So, fact. Here's a fact. If I translate the cosine graph over by 90 degrees, it ends up lying right on top of sine. Cosine of x minus pi over 2, that's the same as sine x. So I demonstrated that graphically. How about I prove it? I can even prove that using facts we already know. So here's a little proof. Cosine of x minus pi over 2 is the same as cosine of negative x minus pi over 2. Because cos is even, right? You can always put a negative in front of the angle and get the same thing. But that's the same as cosine of pi over 2 minus x. But that is the same as sine of x by a cofunction identity. All right, that's one of our cofunction. If you take the complement of the angle, the sine of the complement is the cosine of the angle. So great, we just proved that fact. And I can even say a bit more about the graphs. Let's look at Desmos one more time. So, in fact, now let's look at negative cosine. So there in black, you can see negative cosine. And in green, you can see cosine. And now I'm going to start translating the cosine graph. And it looks like I've shifted it on top of its negative. After 3.17, that's pretty close to 3.14, which is pi. So I've just demonstrated that if you translate it by pi, you get its negative. Fact. Cosine of x minus pi is negative cosine of x. And I won't show you here, but hopefully it's believable. The same goes for sine. Sine of x minus pi is negative sine of x. Cool. Okay. Any questions up to this? So here's a new piece of vocabulary for you. Sine and cosine are examples of sinusoidal graphs. Okay, so they're graphs that look like sine or cosine. And I cannot understate the importance of these sort of graphs in mathematics, physics, engineering, even pure math. they just end up being hugely, massively important because, well, in physics and engineering and applied math, it turns out that almost any oscillatory phenomena can be described by sine or cosine. So that is things that repeat, things that oscillate back and forth, things that move periodically, like anytime you have something rotating or spinning, like on a wheel or a gear or a propeller. Or, here's a big one, anytime something moves in waves. Okay, so I'm not just talking about like ocean waves, but for example, sound. I don't know if you know, but sound is a wave. It's a pressure wave. It's the waves of, it's the frequency of the pressure waves hitting your eardrum that allows you to hear different sounds and different frequencies. Another big one is light. So I pointed out before class started that one student, like, oh, a cute cat, Stephanie. One student drew a light wave as an example of a certain wavelength. So light is a wave. It's a wave of oscillating electric and magnetic fields. So you are going to hear a lot about waves as you continue on in your scientific journey through college. And spoiler alert, they all have sinusoidal graphs. Okay, so you are going to keep coming back to these over and over again. They're also hugely important in calculus. You are going to see a lot of this in calculus. All right, so now let's start working some problems. And I'm going to start trying to graph some transformed graphs of sine and cosine. Here's one of the neat things about this part of the lecture. Technically, all you need to do is remember what your transformation rules are. Right? There's actually nothing new going on here once you know the graphs of sine and cosine. Once you know what the graph of sine looks like, and you know what transformation rules for functions are, you can do this problem. Okay, so I'm not going to be showing you anything that you could not do yourself right here, but I'm just going to maybe explain some of the details and point out a few things as we do it. Okay, so let's graph 2 sine x plus 3. Okay, let's make this 1, 2, 3, 5, -1. Say there's pi, 2 pi. And I'm going to start off by just graphing sine, which we already know what that graph looks like. So the graph of sine, let's see, that goes through those points. Cool. All right, so there's sine of x. So I'm going to use that, and here it continues on. I'm going to use that to figure out 2 sine x plus 3. So first, I'm going to take care of the 2. So first, I'm going to graph 2 sine x, which means stretch vertically by a factor of 2. All the y values get stretched vertically by a factor of 2. So, okay, let me take these y values. Like, for example, right here, we've got the point pi over 2, 1. If I stretch it vertically by a factor of 2, it's going to end up at pi over 2, comma 2. And similarly, okay, let's double all these y values. The zeros don't move, notice, because 2 times 0 is still 0. Okay, so there we've got a graph of, oops, dang it, 2 sine x. I want to point out a feature of this graph, which is a new vocabulary word. That's the distance from the largest value to the smallest value on the graph. That has a name. So the distance from a peak to a valley is called the amplitude of the graph. And the amplitude of 2 sine x is 2. Okay, so here's a general formula. In general, the amplitude of some multiple of sine x is a.
Professor Ciotti, the way that you define it, shouldn't it be 4, or shouldn't it be the distance from the maximum to the midline?
Oh, thank you. Yeah. Good point. Yeah, I drew twice the amplitude. Good catch, Juan. Nice. Sorry, yeah. Juan was totally right. That arrow that I drew was twice the amplitude. There's your amplitude. And Juan mentioned the word midline. So I haven't explained what a midline is, but I think with what I'm about to do next, you'll see what it is. So I just graphed 2 sine x, but the problem also has a vertical shift of 3. So now let's rigidly shift everything up by 3 units. Okay, so I'm going to take each point and move it up by 3. Like, for example, if I looked at this point and moved it up 3, let's see, 1, 2, 3, it now ends up at pi over 2, comma 5. Okay, now let's move every point up by 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 3. 2, 3. There we go. Now let's connect those dots. Cool. So that was a rigid shift of everything by 3, and that then should be 2 sine x plus 3. And notice that sort of the line where the graph is centered at, if you will, like the line that it oscillates around, got shifted up by 3. Let me show you what this line that I'm talking about is. That would be the middle of the graph, or as it's called, the midline. The midline is now y equals 3. So in general, the midline of a times sine x plus, let's say, k is y equals k. Valentina?
So does that mean that the circle's radius would be what you stretched it? Like, would it be 2?
Yeah, good, exactly. So indeed, if we had a circle of radius 2, then at a point on that circle corresponding to angle theta, the y value would be 2 sine theta. Okay. Cool. So that does this one. Any questions on this? How about here? Let's do a practice question. I like sort of challenging you to keep track of the points. Can someone, let's say, this point up here has y value of 5. Can you private message me the x value of that point that I circled? Private message me the x value. And I think I've got about 25 responses. So let's try to get everyone. Okay, so I think about 3/4 of the answers I saw were correct. So let's see. the x value is the x value right there. Okay, we can even compare it to the original sine graph, which on the original graph of sine, here it kind of helps like to, well, one thing you can do is look at what it's between. It's between negative 2 pi and negative pi. So the peak right there, it's halfway between negative 2 pi and negative pi, which means it must be at negative 3 pi over 2. That's halfway between those 2 points. So that should be the x value, negative 3 pi over 2. Okay. Any questions? All right, then let's do another problem kind of like this one. Except now, let's start messing around horizontally. Let's compress it and shift it horizontally. And my challenge now is to graph cosine of 2x plus 1. Okay, so I'm going to start by just plotting a basic cosine graph, which I will perform transformations on. So the basic cosine graph, let's see. Two pi, 3 pi, negative pi. Basic cosine graph. Starts at 1. I always remember cosine starts at 1, and then it's negative 1, and then it's back to 1. Okay, so there's our basic cosine graph. And the first thing I'm going to do, once again, I'm going to handle this in 2 steps. And the first thing I'm going to do is look at the graph of, I'll show you, of g of x equals cos 2x. So how about, just for the moment, let's let g of x equal cos 2x. I'll take care of the shift later. Right now, I need to work on the compression. So this is, this compresses cos x horizontally by a factor of 2. So it's going to squeeze it in like an accordion, okay? Imagine you're holding an accordion in your hand, and you start putting your hands together. It's useful to think about what happens to the period in this situation. So remember that the period, that means how often does it repeat? The period of cosine x is 2 pi. Now, I want to figure out the period of cos 2x. Here's how I sort of think about it when I do this. For the period of cos 2x, this is sort of my thought process when I do this, is I make the argument equal 2 pi. The argument, this is a word I've been using occasionally, by the way. Argument is whatever is inside the function. So, i.e., when does 2x equal 2 pi? And that will be my period. If 2x equals 2 pi, then x equals pi. So that's how I sort of do these calculations when I'm trying to figure out the period. You don't necessarily have to like use that same reasoning. You can use formulas that I'm going to give you, or you can just think of what the compressed graph looks like. But so in my head, I'm going to draw a graph that repeats every pi. It repeats faster. It's a, oh, here's a physics term. It has a higher frequency. It oscillates faster. In fact, let me give you a general rule. The period of cos bx, or sine bx for that matter, by the way. The transformation rules are similar. Is 2 pi over b. Here, sorry. Okay, so now back to drawing the graph. It's not how you spell argument. So I need to draw something that repeats every pi now. Okay, so it does a full revolution in a span of pi. It goes all the way down and up in the period of pi. So it's going to go all the way down and up in the space of pi. Okay, sorry, that looks kind of wonky. Let me try to draw that again. Down and back up in the space of pi. Notice what I'm doing is I'm just taking all the x values of the points that I know and compressing them. Like this point right here, which was pi -1, it got compressed by a factor of 2, and now it becomes the point pi over 2 -1. And you know, like similarly, this point up here, it was 2 pi 1, but now it becomes the point pi 1. Okay, and then after that, it just keeps on repeating. So I can just periodically extend it. And the same thing on the left. Okay, so there we have our graph of cos 2x, which is also what I called g of x. Any questions on that? Oh, okay. I still haven't taken care of the +1 yet, though. So now let me do that. So cos of 2x plus 1 is, here's a common trick that you might have seen in some of these transformation problems, is you factor out the 2. So you write that as cos of 2 times x plus a half. That is g of x plus a half. So now you see why I had to create this intermediary function g, because to get the graph that I want, I just need to rigidly translate it left by 1/2. Okay. So, well, now let's just take every known point on the graph and move it left by 1/2 unit. So, like, for example, 0, 1 gets moved to -1/2, 1. Or negative pi 1 gets moved to negative pi minus 1/2, 1. Oh, wait, what did I do? Right there. Right, just everything gets moved back a half. Okay, now let me try to connect those dots. Okay, yeah, let me fix this dot. Ah, crap. There we go. Cool. Okay, so I moved everything to the left by a half. Why don't we play that game where I pick a point and I challenge you to tell me what that point is. So let's see, what's a point I should pick? How about this point right there? So we know that the y value is 0. Can you oops. Private message me the x value?
Could you zoom out a tiny bit just to see the compression? Thank you.
Yeah, a lot of people are getting this one wrong. I don't know if I've seen a right answer yet. It will help to keep track of like what point was it before it got shifted by a half, and that point was right there, like on the red graph. It was not 3 pi over 2. So let me plot a point on the, let's say like on the red graph. Let's see, that was 3 pi over 2 negative 1, but that's not the point that got shifted. Like what? That point was something 0. See if anyone's gotten it correct yet. Ooh, no, I don't think I've got a single right answer. I realize I have 2 accounts here, so people are sending me chats on 2 different windows. Nope, I don't think I see a single correct answer yet. This is a tough one, I guess. Ooh. So, okay, maybe I'll just do this one then. So here's how I'm going to explain it. Okay, so let's look at the red graph for the moment. The red graph had a peak at pi and a peak at 2 pi. It has peaks every pi, right? Because the period is pi. So it has halfway between these 2 peaks is a valley at 3 pi over 2. Halfway between that valley, oh, this is just going to get messy. Halfway between this valley and this peak is a 0 at, let's see, it's going to be between 3 pi over 2 and 2 pi. What is that? 7 pi over 2? Is that what that is? 7 pi over 2. But that's on the red graph. Did I do that? Wait, sorry. Excuse me, that's wrong. No, sorry. 7 pi over 4 is what I meant to say. Yeah, that's 7 pi over 4 is exactly halfway between 3 pi over 2 and 2 pi. But that's on the red graph, and our graph got shifted to the left by a half, so that means that the point that we're interested in, well, shift that point to the left by 1/2, and what do we get? We get 7 pi over 4 minus 1/2. Ooh. Yeah, that's a tough one, huh? So this was deliberately meant to be a hard problem, by the way, right? Like, I know people like me to do harder examples in lecture. So I try to mix it up, do easy and hard. And we're out of time, so let me just quickly write down the transformation rules for sine and cosine, which is to say, if you're looking at the graph of A times sine of bx minus h plus k, or same with cosine, it's the same rules. Has amplitude A period 2 pi over b, midline y equals k, and a horizontal shift of h. Cool. Okay. So, and we are out of time. Any questions before we stop? Cool. All right, folks. Guess that's it. I'll see you all tomorrow or in office hours.